everyone, welcome to DO Wizards. Now I will be covering the course of electricity which is there in physics honors course in DU SEM-II. Now we are starting with a topic known as network analysis. Now today we will be covering these many topics. First topic is, you can say, your voltage source. Then there's your current source. Then there are your those class 12 you could say concepts of KVL and KCL. Then we will be covering mesh analysis. So let's first proceed with the voltage source. But before proceeding with voltage source, I would like to tell you what this term means, network analysis. Network analysis basically means that we can see from the words which are there in this particular term. Network means the connection of two or more things. And in our case, there are the connection of two or more resistors, which basically make a network. And that network can be of, you could say, rectangular or mesh-like, or you could say of different shapes, but it will be a network. So let's start with the voltage source. So voltage source is basically, you could say, a device. Voltage source is a device that provides a constant voltage. This is important, constant voltage. So this voltage source can further be divided into two parts. You could say there is one ideal voltage source and there's your practical voltage source. Ideal voltage source, you can understand that by a simple circuit. Let's say there is a battery which provides a potential of V. And a resistor is connected in this circuit. Let's say the resistor is RL. Potential across RL is let's say VL, and the current which is flowing through this wires are IL. So if it is an ideal voltage source, there will be no dissipation of current, which basically means that these wires which are in this particular circuit do not have any resistance. So if we apply Ohm's law, we can say that VL will be equal to IL into RL, which will be equal to your V. This is in your ideal case. The voltage across this resistor will be equal to the voltage applied by the battery. So if we consider it graphically, plotting VL versus IL, you will notice that it turns out to be a constant, which is V. And this is because there is no resistance in the wire. If we recall the Ohm's law states that the voltage applied is directly proportional to the current. And in this particular case, we are not having any resistance here. So this particular graph comes. Let's now look at the practical voltage source. Basically, in practical voltage source, we have a dissipation of current. There is dissipation of current. Well, dissipation basically means that the current which has been supplied from this particular point, let's say from the battery's terminal, and the current which is reaching here at the resistor will not be same. There will be some minute difference, not very much, because we are assuming that the wire's length is not very large. So now we were on the case of practical voltage source. In the practical voltage source, we have got a dissipation of current. And so in this particular case, our VL will be equal to the current passing into the resistance, which will be equal to VL minus VS, which is the internal resistance of your, you could say, your battery. So if we see from here, we will get VL will be equal to V minus IL into RS. RS is basically your internal resistance, and the current is the same which is passing through the battery and through the resistor. So in this particular case, if we see the graph which comes, we'll be plotting it in like VL versus IL, which we did earlier as well. So in ideal case, it should come like a straight line parallel to the x-axis, like we had discussed in the previous case as well. But now what happens is that this particular line gets bent towards the x-axis by a value which is IL RS, which we can see from this equation, which is V minus IL into RS. So this is the case of ideal voltage source, and this is your practical voltage source. In most of our cases, we will be considering an ideal voltage source, will not be considering any dissipation, But if in the question it is mentioned that there is some internal resistance, then we will be considering the IL into RS term as well. Now if we see from this particular equation, VL equal to V minus IL into RS. To make VL equal to Vs, what we can do is that we can increase the external resistance very greater than internal resistance. In this particular case, we will see that our external voltage across the RL resistor will be equal to your it will be equal to your voltage applied by the battery. Now let us consider the next topic, which is the current source. Let's see the current source. Current source is basically a device, you could say, which provides a constant current. Now, current source is a device that provides a constant current. So current source also can be further divided, like we had divided the voltage source. It can be ideal and practical. Same will be the case here. In the ideal current source, there will be no dissipation of, you could say, energy, or you could say current as well, because energy in a way implies that your current is getting dissipated. So let us understand this with the help of a circuit diagram. Let's say that a resistor is there is a current source. Current source, we can show it by this particular symbol, which also shows that direction as well. Let's say a RL resistor is connected and the voltage across this RL is VL, and since it is coming towards this side, we will mark it as positive, negative. This will also be positive, negative. Now the IL, the current through this resistance, will be equal to VL divided by RL, will be equal to the current which is being supplied by the current source. This is in ideal case. Well, let's see the practical case. In practical case, what happens is that there is some internal resistance, as we had considered it in the voltage source as well. So let us draw the diagram for it. Same RL, the voltage across this is VL, and some resistance will also be there of this current source. It will be RS. Current is supplied of I. Here it comes, let's say IS. Here it comes like you can say IL. Now applying Kirchoff's current law at this particular junction. I will be discussing Kirchoff's current law later after discussing this. So IL will be equal to I minus IS. This is from Kirchoff's current law. So IL, you can write it to be I minus IS. The current which is passing through the RS will be nothing but VL divided by RS, because the same voltage will also be applied across RS, since RS and RL are parallel, that we know. So this is the case of practical current source. As you can observe that here IL is equal to I, here IL is not equal to I, because there is a factor which is introduced, which is VL divided by RS. So if we consider the diagram for this, plotting it between IL and VL, for ideal case it will be a straight line, because IL is equal to I, and for the practical source it will be at an angle towards the x-axis, and the shift, you could say, will be VL divided by RS. This is your ideal case. This is your practical case. To make it ideal, you could say the current source ideal, will have to make RS very greater than RL. And why it has been, you have to do so? Because if you make this particular condition, then this term could be neglected, and then your IL will be approximately equal to your I, which is the condition of your ideal voltage source. Now let us consider a few rules as well, which we will be using in our further topics. First rule is your voltage divider rule. This rule you all must also have studied in class, you could say class 12th. I think it's also taught in class 10th as well. So let's say a voltage is connected here, and many resistances, say R1, R2, R3, so on up till Rn, are connected in series. So considering the voltage across the first resistor, we can write it as V1 equal to I R1. Well, I is the current which is passing through this whole circuit. So I, we can write it as, from Ohm's law, we can write I as V divided by R equivalent. R equivalent is the net resistance of this circuit into R1, where your R equivalent will be equal to R1 plus R2 and so on till Rn. Why I have done so? Because all these resistances are connected in series. So from this particular equation we can say that in general Vn will be equal to V divided by R equivalent into your Rn. This is basically your voltage divider rule. Now let us see another rule, which is the current divider rule. Let us see the current divider rule. Let us draw the circuit. Let us draw the circuit for studying this particular rule. In current divider rule, we will be considering a current source. So let's say that we have got a current source which provides a current I, and the resistances are connected, let's say, in parallel across this current source. Or let's say n resistances are connected, so on and so forth up to Rn. Current passing through this R1 resistor is I1, through R2 is I2, and through Rn is In. Let us consider the voltage difference across this particular current source is V. Same will be the voltage difference across every resistor which is there in this particular circuit. So I1 you can write it from Ohm's law as V divided by R1, and V you can write it from Ohm's law as V equals to IR. So in our particular case it will be I into R equivalent. R equivalent is the net resistance of this particular circuit divided by R1, where your R equivalent you can find it from this particular formula, 1 upon R equivalent equal to 1 upon R1 plus 1 upon R2, so on and so forth up to 1 upon Rn. Now you can write the current I1 as I into R equivalent divided by R1. Your I2 in similarly will be written as I into R equivalent divided by R2. So generalizing it, you can write it as current through nth resistance will be equal to the current into the R equivalent of the circuit divided by Rn. So this is your current divider rule. We will be using these rules in solving the further problems.